Good afternoon, ladies and gentlemen. So, in this afternoon, it's our great pleasure to invite Professor Tanihata to give the open seminar. This is the 61 open seminar of the frontier in nuclear physics of Fudan University. This seminar is organized by in the Institute of Modern Physics, Nuclear Science and Technology Department, and also the key laboratory of nuclear physics and ion beam application of Ministry of Education, and also NFC Shanghai Research Center for Theoretical Nuclear Physics. It is also co-organized by Nuclear Science and Technique and Nuclear Techniques, and also co-share. So first, let's briefly introduce Professor Tanihata. Professor Tanihata is a professor in Beijing University now, and also a special appointed professor in RCMP Osaka University, Japan. He has been worked in various fields of science. So Professor Tanihata obtained his bachelor, master, and PhD degree in Osaka University, and worked in many famous university and laboratory in the world, like in University of Tokyo, Lawrence Berkeley Laboratory, and also in Reagan. And he have obtained many important honors. So like he obtained the Miller Award in 1975 and the Nishina Prize in 1989. He got the PS Fellow in 1994. And also many other honors. Like in 2010, he got the Southern Talent Program of the Chinese government. He have achieved many discoveries, especially we are well known, like the discovery of neutron color, neutron skin, and the new excitation model in neutron-rich nuclei. He published in total more than 460 papers, and the total citation in Google Scholar is more than 27,000. And his H index is 79, and also he is listed in the world top 2 scientists of Stanford University in 2000 in this year. So now let's welcome Professor Tanihata to give this open seminar.
Thank you very much for nice introduction. I'm very glad to come here. Actually, I have not been here for a long time. I've been in China for more than 10 years now, but I have not been in this university yet. I'm very glad to see those young people here. And today I want to talk, at the end, I really want to tell you that the nuclear structure physics, I concentrate on nuclear structure physics today, but nuclear structure physics really need revolution now. We have to change. In particular, theoretically, you have to deal with a very important question. And to reach that, I go back about 30 years ago, where we started this experiment of exotic nuclei far from the stability. And I show you briefly, and today I don't go into the detail of the experiment at all. I tell you only the result of the experiment. What does that mean in physics? And go into the importance of theoretical consideration. Okay. So I start from the very old time when I was a postdoc, and after that I went to Berkeley and started the new experiment using beam of radioactive nuclei. Maybe now it's almost common using radioactive beam, but 30 years ago, there's nothing like that. I just started. And before that, because after Rutherford, you know that you have to make scattering to study nucleus. Okay? You have to make nuclear collisions and observe the reactions. And then, of course, at the very beginning, you have to accelerate some beam that you have to bring from somewhere. So it's a stable nuclei. Only stable nuclei can be scattered. So you can study only stable nuclei. And if you want to just see the size of the nucleus, how large is the nucleus, you have to make collisions. And until 85 or so, this beam was only stable nuclei. So the stable nuclei has been studied very well until 30 years ago, but nothing has known for unstable nuclei. Just even how large is the nuclear size for unstable nuclei was not known. So this is really a new thing at that time. It's not new now. So we just made experiment. How large is the reaction cross-section, interaction cross-section? And then started to measure the size of the nucleus. Now, that makes a big change in nuclear structure physics. Okay? Before that, this was known as common properties. This is really considered basic property of nuclei. That is the radius of nuclei. Nuclei is roughly round shape, and radius is proportional to the mass of the nucleus, a to the 1/3, and then surface is going, density is going down. This is called, how thick is surface is called diffuseness. And this diffuseness is constant. Any nuclei has same surface shape. And third is nucleus is, of course, made of proton and neutron. And proton and neutron density are all same. Even if number is different, the shape of the density is same. And this was common. If you see the textbook before 1990, it is known in the first 10 pages of textbook. Okay? And this really is understood theoretically by saturation of the nuclear density and range of the nuclear force, how long nuclear force is there, and strong PN attraction. Attraction of proton and neutron is stronger than the attraction of neutron and proton-proton. So with those properties, people believe all nucleus has this property. But then when we started to measure the size of unstable nuclei, suddenly everything has changed. So this is just the figure showing the nuclear size in nuclear chart. So those blue are stable nuclei. Those size very follows that a to the 1/3 dependence. But now if you see the size of the nucleus along this line, so this is same mass number. And you see that this is much larger than the size of nucleus here. So it's already with same mass number A, size is different. That already breaks the first line of that common rule. And next one is that we measure this density distribution. The common old rule is that should be same for all nuclei. But now you see that some nuclei has density going down very quickly, but some of them have very long tail. I discussed this one a little later, like very long tail. So this shape is different from nuclei to nuclei. Okay. Now, third one here, this is the size, radius of proton distribution and neutron distribution measured in sodium isotope. And they are not same. So this means all of this rule is not true for unstable nuclei. That rule was common only for stable nuclei. So that really started new physics in nucleus. And we had to restart to consider those things. And then many things has been discovered. So one is this long tail. The most famous one is lithium-11. It is called neutron halo. It has long tail. So size of lithium-11, mass number 11, is almost as large as lead 208. So it's huge, although it's very small number of A. So it was very big, and this is called neutron halo. And so, and there, this seems like only neutron has long tail. Proton is only inside. The proton and neutrons are not together, although they are very attractive, but they are separated. And another interesting thing, this is in quantum system, only nucleus, this system exists. That is called boromian. If you see those three rings, none of them are interlocked. It's not connected. You see this? Red one is just above the green one and below blue. You see it? It's not like this. It's just on top. But if you put three, it's bound. You cannot take out. This is very funny system. Okay? So two are not bound, like neutron and neutron are not bound. And lithium-9 and neutron is not bound. Lithium-10 is not bound. But if you put together two neutron and lithium-9, you can make lithium-11 bound. And that makes this halo. It's very funny, interesting one. And actually, this is a classical boromian. And classical mechanics, you can make boromian. But in quantum mechanics, there is no boromian observed. Only nucleus has boromian. And many nuclei are like that. Not only lithium-11, helium-6, helium-8, and barium-14, and many of them are. Okay. So, and another very interesting thing is that the mixing of this is in lithium-11, very different orbital. P wave and S wave, they have different parity. They mix together very much. And this, I will go back later Maybe for you it's a little difficult to understand, but anyway, there's such kind of mixing edges. And another thing, I go back to this halo. This seems like this is found for the first time in nucleus, but now it become very popular for other fields, also in atomic physics or molecular physics. They start to find it. This is helium dimer, helium atoms. 2 helium makes binding state. For a very, very long time, they consider that helium doesn't make molecule. But recently they observed helium 2 molecule. It's called helium dimer. And then their halo. This figure is very interesting. Here, this is the potential of helium and helium interaction. And this is van der Waals interaction. Exchange the electron. It's in this scale, it's very short, like angstrom. But their wave function extended up to 200 angstrom. So this is all halo. And this is the application of halo. If you observe how long is this tail, you can determine the binding energy of helium-2 dimer. And actually, they found that it's bound only by 150 nanoelectron volts. Very weakly bound state. So it was so difficult to observe. But now they know it is. And this is one of the applications of halo physics in molecules. Okay, so now I go into more for today's talk. This is another thing. You know that in nuclear physics, nuclear structure, shell model is one of the most successful model. And even if you use other models like mean field models or initial models, anyway, you have to discuss the shell structure of the nucleus. And shell structure is in stable nuclei, you know that in this region of nucleon number is up to 6. It is in P shell, and below that there's S shell, and P shell is here, P1/2 shell is here, and above that D5/2 and S1/2 and D. So this is normal shell structure, every theoretician knows. And that is true for those stable nuclei that you see those states. And magic number is the one that, like here, 8 or 2, nucleus is very strongly bound. Now, that is considered before that those shell closure is very strong and doesn't change even you go to the neutron-rich nuclei. But actually, it was not true. One very important and obvious one is helium-10. Helium-10 has a 2 proton and 8 neutron. So it is so-called doubly closed shell. The proton and neutron both are closed shell, magic number. So it must be bound very strongly. But actually, it's not bound even. So it was a mystery why helium-10 does not exist. And then this study really found that in this region, magic number 8 is very strong here. For example, oxygen 16 is doubly magic, 8 and 8. So it's very strongly bound. But then if you bring down, then it's not strong anymore. And in this region, as I said, in lithium-11 is here, different orbital comes in. Here, it's very funny thing that this, I said, it's a mixing of P wave and S wave. P wave is here, so it's natural. You see P wave, but S wave is here. In usual order, it's much above. But this orbital is in lithium-11. Very funny things happens. So here, closed shell is completely broken. And in other regions, there are something more interesting is happening. Okay? So this is one of the very interesting things. It really occurred and found like 20 years ago or 10 years ago. So if you see more that this oxygen 28 is another doubly closed shell, 8 and 20. 20 is calcium 40, it's very strongly bound. And this is, again, another doubly magic, but it doesn't exist. It was a long question. Why this doesn't exist? It's like helium-10. And instead, n equals 16 become magic number. N equals 16 near the stable nuclei is not magic number at all. But here it becomes strongly bound and make a magic number. And such changes are occurring in many neutron-rich nuclei. So this is the sort of result until, say, 5 years ago or so, that we have to really consider why this is happening in neutron-rich nuclei. Now, there are many theoretical models trying to understand this region and trying to understand this region and trying to understand this region. This is another important region. It's called deformed region. But there are many. But today I want to talk that if you put one new ingredient in theory, we can understand most of those things. And that is the most important message I want to tell you. But that is not really included in many of the nuclear models. So I really want to tell, it is really important to include this new interaction in nuclear structure. Okay, so this is my goal to tell you one important thing. Now, one thing we have to be careful that what is stable and what is unstable, where we study. Here, I just wrote one very suggestive figure in whole nuclear chart. Here, those red region, those nuclei, proton and neutrons are occupying same shells within same major shell. Here, proton and neutron are both p shell. Here, proton and neutron are both st shell, both f shell and such things. Now, those green part is that proton is in p shell, but neutron is in SD shell. Here, this is another one. This is SD, proton is SD shell. This neutron is above that, P shell or others. Now, if you see the nucleus, most of the nucleus, we observe this. For stable nuclei, proton and neutron occupy similar orbitals. And next one is that neutron occupy one shell above. This is very important. And two shell above, there's only a few nucleus we know. And actually, this is the region, it's not known at all what is going to happen. But funny things always, those new things always happens in here, in this region. When it's changing, neutrons start to fill next shell. But this is very important thing. Now, so before I go to my our model, that I have to use this ab initio very great work of Argonne theoretical group. They made, this is, I think, the real ab initio, because they use the nuclear-nuclear interaction obtained from the experiment and use real ab initio calculations. Then, but calculation is so complicated that they could calculate only up to carbon-12. After 30 or 40 years, they are doing long calculation, long time, spending time, but calculation could be done only up to carbon-12. Even oxygen-16, they are not finishing yet the calculation. But very important conclusion of them is that for binding energy, how nucleus is bound, 80% of the attraction comes from pion exchange. This is really important result. And so we believe in this, okay? So essentially, we consider the interaction of pion exchange. I don't mean one pion exchange in 1, 2, 3, or. Then pion interaction itself is this pseudoscalar pion is exchanged. So you have this operator. And then naturally, it comes central force and tensor force. Now, important thing is this central force is, of course, depend on spin interaction. And tensor force depend on spin and also coordinate, relative coordinate. Tensor interaction depend on the direction of the spin. Now, difference is that this interaction has this Q square term. Q is momentum transfer. When it goes this way, how much momentum it carries. Okay? So if you carry more momentum, you have more attraction or repulsion, stronger interaction. But central force doesn't have this Q square term, and then it's stronger at zero momentum transfer. This is very important. So now most of the nuclear physics model doesn't include tensor interaction explicitly. People consider tensor interaction is included and make some potential or something, but not explicitly treated. But central interaction is explicitly treated because people consider that nucleus, we are studying this low excited state, near the ground state. And so many people consider as long as you discuss ground state or low energy excited state, you can ignore the detail of this. Of course, it is included effectively, but it's not explicitly used. I'll tell you a little more about that. So this is important. Low energy, this is more important, and low excitation, this is more important. High momentum region, this is more important. I skipped this one. This is theoretical detail. So no theory treat tensor force. So we have to include those high momentum thing. What is going to happen? Okay. So this is the statement for theoretician. Please include the tensor interaction explicitly in your calculation. I know it is very complicated and difficult. Now, so I just go several examples of the importance of tensor interaction. And it is very well known. Neutron is not bound without tensor interaction. If you use only central interaction used in shell model, neutron doesn't exist. You have to put, and this is the really ab initio calculation, how neutron is bound. Now this is the binding energy, of course minus is bound, and kinetic energy part is this, and central interaction gives this. Okay. But this is much smaller than the kinetic energy, so it's not bound. If you put tensor interaction, that makes big attraction. And finally, this is more than those. Okay, so only if you add this one to the central interaction, neutron is bound. Now, the important thing is that this tensor interaction gives energy from, this is S wave and D wave mixing. So what is D wave? If you put in shell model view, just to explain, okay? Now, if you put proton and neutron in S wave, and that is this, that gives this energy. If you put in, next one is in P shell, you put both of them to P shell and make D wave, relatively E wave. This will give some amount of binding. But here, tensor interaction gives this big energy for this cross term. This means when those particles excite to that one, you gain energy. This is transition energy. It's not usual diagonal energy. It's non-diagonal energy. And this is very important. You need D wave. And this D wave component is not much. It's only 6%. that gives big attraction. But don't consider D waves is giving attraction. It's a transition from S to D. It's giving attraction. This is new type of energy. And if you see the wave function of this S wave and D wave is smaller. If you consider in shell model with same potential, of course, D wave has to be larger. But D is much smaller. So it's very close together. And that is, the tensor interaction is has shorter range. Central interaction has repulsive core, so it's far. And if you include tensor interaction, they come closer. It's tensor correlation. They are closer. So you have to treat this as much closer system. And this is the neutron. Yes.
Central force at the repulsive core is attractive at large distances, but the angle force is purely attractive, right?
Not necessarily. It depends on the direction.
Yeah, it's
yeah, this one is attractive. Yeah.
Really attractive.
Tensor force is attractive and repulsive. It depends on the that's
direction.
Tensor, yeah, it's in depend on this direction, orbital and spin direction. But this potential shape before is negative. So what I want to say is that in this figure, tensor force is short range, and attraction is strong. Repulsion is also strong.
How are these two potentials constructed? Do you have in logical construction, or can be derived from more elementary theory, like from quantum physics?
It is with elementary theory, as I showed. It has large transfer momentum, gives you larger energy. That means larger momentum transfer means short distance. So that's the relation. So it's theoretically, if you do make a quark exchange between nucleon, you can get that property. Roughly, I mean, it's still those calculations are under progress, but I think tensor force comes naturally from quark exchange.
Verified by that is,
yeah.
That is the calculation?
Yes. Yeah. I forgot the name. Japanese is doing this calculation, and it's for two-body interaction. It has been already proved.
That's another. Except for higher exchange because of those fields. That's another measure exchange that is
other sigma, rho, and those exchange can make tensor interaction too. Yes.
Yes.
But that's why I said at the very beginning, for nuclear binding, 80% of energy comes from pion exchange. That's why I'm talking about this. And I don't know about the other mesons effect. Yes, that's unknown. It's important, maybe important, maybe not. Okay. Thank you. That's very important thing. And So this is our initial calculation that is giving D wave is much short range. Now, we know this very well. But none of the nuclear modeling these days use this part at all for binding, and except those of initial calculation. And so there is one model that somehow effectively treat this interaction as of initial way. And this is called tensor optimized shell model. This is Myo, Toki, and Ikeda. They developed this. And what they did is they include this two-particle two-hole excitation. I'm mixing the word of the shell model and the initial model, but sorry. This is in shell model that is excitation to this. So this is two-particle two-hole excitation. They included this part explicitly in the basic wave function and solve the nuclear structure in ab initio way. But one trick is that, as you see from argon calculation, this potential should be narrow. And you don't know, of course, how it depends on the short rangeness of the tensor interaction. So they just made this size as a variational parameter also. So they, for excited those two-particle two-hole level, it's not necessary to have same potential width. They just minimize the energy to make that. And so as an interaction, they include central and tensor and LS term and Coulomb interaction as usual. But the point is, treat the tensor explicitly, they use this excitation and change the effective range of the interaction. So what is the selection rule for this in nucleus? The one of the important thing is that you need two pion exchange to make this D wave possible. Okay? So essentially, you have two nucleons excited by pion exchange, and another pion exchange returned to a user state. Now, in nuclear physics, the many models use only low momentum nucleon, assuming G metrics. G metrics include all the 1 pion, 2 pion, 3 pion, everything, or many others, as one blob. And because of that, those nucleon has to conserve momentum. So in the calculation, you can include only nucleon of momentum in shell model. Only low momentum nucleon is included if you do this calculation. Now, if you do this calculation, of course, I mean, momentum has to conserve here, but here, this is intermediate. Momentum can be anything. So you can include very high momentum wave function in here. And that's why tensor force becomes stronger in here. If it is only one, you cannot make high momentum transfer. But because of two, you can make it. And so this is how why they included two-particle two-hole excitation. Now, selection rule, this is very important for my discussion later. Selection rule from here to there, it should scale. So you cannot change J, and this particle, this particle. J is same, and spin flip and change of orbital angular momentum 1. So S wave goes to P wave, but spin flip, two particles, spin flip. Okay. Now, if you consider two particles from here, those two particle state should have no change in total J. Spin change has to be 2. Delta L has to be 2. So this is the selection rule of this two particle two hole excitation. Yes.
By exchanging two parents instead of only one parent, you can go high momentum process tensor, short distance tensor interaction.
Yeah.
Also understand this. Can understand this process in a following way by exchanging two parents. That means effectively you're exchanging the raw metal or signal metal that has a larger mass. So that's by using the Heisenberg uncertainty principle.
That's the problem. If you make sigma here, you cannot change momentum. I mean, you cannot include high momentum in the where there's no high momentum nuclear. Then tensor interaction is weak. That's the point. You need this part, virtual excitation. That's the big point of this discussion. And only one thing you can do is if you do some exchange. And then, of course, you can make momentum transfer twice as large as film motion. And that is what Otsuka is doing. Otsuka include in one pion exchange and exchange term, including tensor. And that has some important effect. And that is true. And that is not wrong. That is right. But this one is not. It's essentially this part has to be included. That's the difference. Go.
So let's get understand why by exchanging two terms again.
No, because you can include in here a high momentum nucleon. In this virtual state.
Just by exchanging two parents.
Yeah.
High momentum exchange.
Yes. Yeah. Only if you make off-shell wave function, you can include high momentum. Just momentum conservation is fulfilled with it. Okay. And now let's see the effect of tensor interaction for a little more nucleus. Deuteron, you may think it's too simple, but alpha, this calculation has been done. Of course, alpha is calculated ab initio calculation, so it's well known. But now this using that tensor optimized shell model, they did the calculation, and this is the way. Now they reproduce the binding pretty well, and here, what is written here is this is the inclusion of intermediate state or how much higher state you include as an excitation. Okay? And so this is classified by the L max. If you include up to 2, 4, it's very high excitation energy. It's essentially like major shell. Now, kinetic energy, and here, this is the binding energy. It goes to, this is real ab initio, result of ab initio calculation. So it's very well, slightly different, but it's very well converges to the good number. And inside there, this is a central interaction. And this is tensor interaction. So as you see, at very low momentum region, tensor energy is almost 0. And with that, you cannot make nucleus bound. It's unbound. So if you include higher excitation, tensor force become stronger and stronger and stronger. It's almost as strong as central force if you include all high energy state, and makes alpha bound. So this is the reality and consistent with ab initio calculation. So now you know that this calculation of tensor optimized shell model pretty well reproduce ab initio calculation, but it's shell model type, so you can do some calculation. Now, remember, if you include just one more major shell, so like in neutron, I said that from S to P is important, but actually it's in alpha case more important going up more and more. Okay? But the point is, just including one more major shell makes already more than 10 MeV binding. So it's just making one major shell transition, you gain 10 MeV. That's a lot. And actually, if you see the mixing, many mixing state, this is L, one more major shell, two more. Many, it's so many mixing of them. But among them, I just see those excitation to P shells. Now, this is the mixing. This is the all S wave and P1/2 mixed with this spin and I spin combination. And those are all mixed state in one major shell up. Now, what are the contributions from those? So this is giving only, this is all binding negative, but you see that this one is giving main attraction. And this is, as I said, the two-part group from S wave to P wave transition, and spin 1 goes to spin 1. So essentially, neutron wave function, S wave, proton and neutron, this is I spin 0. So it's Pn pair. Pn pair of same spin goes up to P shell and spin comes down. So that is really the selection rule I showed. Spin changes 1 and two-part groups of spin, delta S total is 2. And L is two-part group from 0 to 1. So delta L is 2. So essentially, this transition is giving most of the transition energy. I said about more than 10 MeV is coming from tensor, from 1L. That is almost all from this. So that is very important. So if spin, this is proton-proton or neutron-neutron pair, this transition doesn't give because it's not tensor interaction. So this is very, very important. And okay. So if I generalize that, again, this is very important. Pn pairs from this orbital goes to one major shell up and L equal +1 or -1. That is the largest transition. The point is that it changes L, but doesn't change J. So it goes from S1/2 to P1/2. It's same J. So in S case, it can go to P wave. From P, you can go to S or you can go to D. Okay. So that is this rule. So this transition is spin, flip, and this. And it doesn't go to here because it changes J. Okay. Same J. Okay, now I go to very classical question of theoretical model. Ikeda, this famous Ikeda and Horiuchi, always tell me there's no interaction that can explain carbon-12 and oxygen-16 together. If you explain carbon-12, same interaction cannot explain oxygen-16. If you explain oxygen-16, carbon-12 is not. And people think because of alpha cluster is the reason in carbon. But is it true? Or what is basic? And that is reason, but now I explain with this tensor interaction. Now, this is the consideration of rocking. Okay. Now, if you do carbon-12, those proton and neutron can excite to P1/2, okay, as tensor interaction. And those P wave nucleons is excited to the D wave, D3/2. Okay. This is only mixing by tensor. So you gain a lot of energy by this transition. Now, oxygen. Because you feel P1/2, you cannot excite this. So you lose 14 MeV with this. I mean, it's not exactly 14 MeV, but the similar energy. So you lose this, but of course, you gain the transition from here to there. But the interesting thing is if you feel proton and neutron in same level, you have new type of tensor interaction going up. One more. major shell, but you close this, block this. So essentially starting from oxygen and above carbon-12, those nucleon has different behavior for making attraction inside the nucleus. That's why it suddenly changes. Here, effective interaction loses one big element. And that's why carbon-12 and oxygen-16 cannot be explained in same effective interaction. Now, if you go more, calcium-40, now, many of them are blocked, but many of them are opening. So essentially, this is the saturation property of nucleus in the way of tensor interaction using shell model view. You know that from the very beginning, nuclear saturation in film gas occurs by tensor interaction, not by central core, central repulsion of this. So remember, Beth already told that nuclear saturation occurs due to the tensor interaction because of the blocking of this. So actually this happens all the way, but this blocking starts at oxygen 16. So this is very, very important thing. And because of that, you are gaining more tensor energy, losing tensor energy. So actually it's saturated. It becomes almost constant. So that's the nuclear property. For stable nuclei, if proton and neutron number is the same, that is true. So this is just, I summarize that this produces both interaction and tensor force is gained by the transition of p-n pair to higher momentum state and under selection of this. But tensor interaction is blocked when nucleon occupy higher orbital. Thus nuclear saturation occurs. Now, this high momentum nucleon, is that really exist in nucleus? Yes, we know. I'm taking so long time. I skipped this part. It is observed by several experiments with electron scattering and also PPD experiment. But the point is this. This is the statement. It has been taught long time. You know that the spectroscopic factors in shell model is always 80% or lower. And some 20 or 30% is missing somewhere. And that is the conclusion of electron scattering. That always you lose some part to somewhere. But now, my question is it just losing spectroscopic factor and do nothing to the structure of the low energy state? And my answer is, it is affecting the structure with this thing. Now, this is the thing. If you go to very neutron-rich nuclei, it's like this. Okay? So what is the difference between this and carbon, calcium-40? Calcium-40 has protons in here. So it has tensor interaction going up. But now if neutron-rich nuclei, this is important, that neutron occupy one major shell above. So neutrons are here. All tensor is blocked. You cannot tensor in one major shell. You see that you cannot bring this one, and doesn't make new tensor interaction at all. So oxygen 28 is the nucleus that lost the effect of tensor interaction in one major shell transition. And that's why it's not bound. It loses big energy from tensor. Obvious. If you agree. So this normal nuclei has blocking and opening. This one has only blocking. That's a big problem, a big difference. So just use this speed and just only one major shell above. All neutron-rich light nuclei fuse delta L equal 1 orbital, and then it blocks. Of course, it's not zero. I mean, actually, more higher transition is mixed. But that part, as long as the nuclei we know, we don't change. The neutron never goes two major shell above. So it's only until this part. So we just consider this part as Q space, for example. But this space is alive. You put neutron or remove neutron. So just consider in this way. So just remember only this part. We are discussing only this part. Okay? Because those parts above two major shell above, it's always there. Because any nucleus we know now doesn't fill that part. So this part remains, but this part changes. But it's already 10 MeV. It's a big change in nuclear structure near the ground state. So just consider we have some potential made by central interaction and everything, and about the tensor interaction above two major shell. And consider how it changes if you change the number of neutrons in one major shell above. Now, we have to change the meaning of magic number. Magic number is where energy gap to next nucleus or orbital is wide. Okay, okay, just we consider this mean field and delta equal 1. Okay, so this is roughly calculated energy of this transition. So it always like several MeV changes if you block. Now, just consider why doubly magic helium-10 and 28 are not bound. Helium-10, if it exists, this has to be P. Then that blocks here. And actually, this is the mass number, and this is binding energy. So this is a single particle orbital in each section. And this is around well-bound nuclei, 6 to 8 MeV. And this is very loosely bound nuclei. If you go to neutron-rich, it's loosely bound nuclei. Now, in helium-10, helium-8, this orbital is very loosely bound. And if you block tensor interaction here, like 10 MeV or so, it just goes up. So if you lose tensor energy, this orbital goes up. It is difficult to explain. Orbital doesn't go up. If you put particles, total binding energy goes up. And because of that, helium-10 become unbound. Just goes up. Helium-8 plus 2 neutron blocks this and goes up. Now, oxygen-24 is also here. D wave. If you feel D wave, it goes up, unbound. Now, why calcium-48 is bound? It's like asymmetric on state. But it's interesting. Now, the point is, calcium-48 is F7.5. F7.5 is not used by the tensor interaction from the beginning because there is no state of J7.5 below. So, filling this doesn't block any tensor interaction. And when it starts to put P3.5, then mixing from this one is blocked. So actually this gap becomes even wider. So that's why calcium-48 is very good doubly magic number, although it is asymmetric. The important thing is now the new information is this lowest orbital in new major shell always has largest spin. This is not used for tensor. So filling it doesn't make tensor blocking. That is why JJ coupling scheme works very well. The lowest orbital is always good. Doesn't destroy the tensor interaction. So those three magic numbers are explained. Now, so new magic number appears in 6. That is because P3.5, filling P3.5 doesn't make any blocking of the tensor. Again, below that is only 1/2. But if you start to fill P1/2, it goes up. So this gap becomes wider. And that's why n equals 6 become magic number. Now, this is interesting. If you start to fill this one, you have this one, gap is large. And if you start S wave, it goes up. So it's always like that. If you start to fill orbital energy gap increases. So that's where exactly those magic number appears. And this is essentially the same thing, that the magic number 8 and 20 disappears because 8 is here, but if you put some particle, then it goes up. So the gap here becomes narrower. Or sometimes it may even come higher than this. 20 is also true. 20 is that if you put particle in here, it goes up. So that the mixing between D and F occurs quickly. F is not affected. This detail you may check it later. Now, another interesting thing is why oxygen stops at 24 and fluorine continues to 31. Only one proton. And that is exactly the same reason. If you put one proton, you start to gain a lot of new tensor energy. But oxygen, you don't get that. You just block, but with fluorine. And it goes on and many things. And this is mixing of lithium-11 and barium-12. Those why mixing occurs in lithium-11 is here, just because this goes up and become very close to S. S is lower here for weak binding energy. This is the effect of neutron halo. It's more bound. And then if this one goes up, it becomes very close. So they are mixed very strong. But then if you go to barium-12, it's more bound from beginning. So D wave is lower. So if you bring D wave higher, then you start to see D wave component of D more. So, and I just went more quickly and quickly, but now it's important that the importance of tensor interaction is really there. And it changes the orbital contribution of orbital. The nuclear structure changes because of this tensor blocking. And the effect of recently observed high momentum PM pairs are considered in relation to nuclear structure, not just only existence of high momentum, but it affects the structure of ground state and low excited state. And the point is blocking. If you put neutron, you block tensor. And that's why you lose energy. And this is very significant in neutron-rich nuclei. And it is because proton and neutron are asymmetry, not symmetry. Okay, so so it's very important to include that. But if you really want to do this calculation, you have to include this tensor interaction, including high momentum component. Unless you include high momentum component, that does not affect. So actually, I just I explained those things, and it's very, very important. But even unfortunately, this TOSM calculation, shell model, but still cannot go more than carbon 12 and oxygen 16. This computer time, because you have to include high momentum part up to 12 h bar omega or 18 h bar omega to have a good conversion. So the calculation is very not complicated, just tedious, time consuming. And because of that, for heavier nuclei than oxygen 16, theoretical calculation has not been done. And I think we require some sort of new method to treat this high momentum component quickly. And I think it's not really a detail of the calculation. It's very, as I showed, very global change of the structure can be considered in this. So I really hope theoreticians really look at the tensor interaction very carefully and include them explicitly. And it's not easy task, but I think for coming nuclear structure physics, we really need that. And so then because of that, I consider that drip line may be closer than present predictions without tensor, because tensor blocking comes more and more and more and more. And I predict next magic number. And this is important. Our process. Now I'm talking about the application of nuclear structure physics to astrophysics, and neutron-rich nuclei is very important for our process, for example. But the structure really strongly depends on the tensor interaction. And so it's really important. Okay. Another thing I didn't talk about is LS interaction. And actually, it is known from the old study of Arima or those people, the half of the LS interaction may come from tensor interaction, half. But remaining half are not known. And it's a nuclear-nuclear interaction. LS term in nuclear-nuclear interaction is not enough. So this is another big question that you can really, because this is very much related to the discussion I gave. I treat that this doesn't change for neutron-rich nuclei, but this may changes. So there are those questions that we have to answer from now. Okay, so those are theoretical colleagues in Toki and Myo, Ikeda, Horiuchi, and experimental collaborators are here. Okay, thank you very much.
You are very detailed, especially the tensor that you can see.
May I have
Yes.
a question?
Yeah. Who is
Hello?
talking?
Yeah, please.
Hello. Thank you very much, Isao. I'm Yu Zhang from IMP.
Okay. Go ahead.
Yeah, very nice talk. And but for me, it's not easy to understand clearly.
I understand.
I have several questions. So the first, you mentioned that PN attraction or high momentum PN pairs. So here you mentioned that it is a bare PN interaction or it's a radial PN interaction.
What do you mean residual? It's not effective interaction. It's PN pure interaction.
This is so. So here you measure it should be a pure PN interaction, right?
Yes. Yes.
Okay. So okay. So in this case, my second question will be. So I like to ask you how to can we deduce this kind of PN interactions by using the mass data? So this means cannot, right? We cannot.
At this moment, I have no idea. But of course, you also some mass people are discussing this PN pairing interaction, right?
Yes.
For heavy nuclei. At this moment, I have no direct connection to that, but it may be related because PN pair is behaving differently in Z equal N nuclei. So, but it's a question that you can keep asking.
Yes. Okay. Another question is, so you talk about the high momentum PN pairs in the neutron-rich site. What about the effect of such high momentum NP pair for the N equal Z nuclei? It still has some consequence because in N equal Z nuclei, there is a famous phenomenon so-called the Wigner energy. So if the Wigner energy has some relations with the high momentum NP pair.
That again, good question, but I don't think it is related. Wigner term is sort of low energy collective phenomena. And this P pair for Z equal N has been done by Terashima. We are doing this experiment in oxygen 16. Actually, tensor interaction is strongest in N equals Z nuclei. And he's doing PPD experiment for high momentum transfer and finding tensor interaction is very important. But low energy character, this Wigner term, is related or not. I'm not sure at this moment.
Okay. The final question is because you are founder of the neutron halo nuclei. So now my question is, now if there is, I heard a lot of people talking about the proton halo, but now if there is a definite confirmation for the proton halo nuclei in the proton-rich site nuclei.
People consider that boron 8 is a good proton halo example.
And also the neon 17.
Neon 17. No.
Neon 17.
Neon 17, yes. That
neon
is
17. Because they measured the charge radii, right? And no others. No others?
At this moment, no real candidate at this moment.
So in this case, another question is how to define the halo, the proton halo. What is the definition of halo? Because I saw some publications talking about the matter distribution or the charge distribution. It gives a tail usually. So what's the difference between proton halo and neutron halo? I also heard that they say in the proton-rich site, there are Coulomb barriers. So the extension wave function is very much limited. So the halo is not a halo. But what is the definition of the proton halo?
Okay, halo is not well defined after 30 years. But the point is that we usually says that how many percent of the wave function is outside the potential.
Yes, please give me the figure.
It's more than half of the wave function is outside. Okay,
more than half.
Yeah, and the point is, of course, in the proton side, there is a Coulomb interaction.
Yes. And
halo becomes shorter, and I don't think we are really checking this same property for proton-rich side.
Oh.
And the reason why we don't observe in heavier one is because Coulomb barrier become higher and higher. That's our understanding at this moment.
Okay. So by the way, where are you now? You are in Beijing or in Japan?
I'm in Fudan University.
Now you are in Fudan University.
I'm in Beijing.
So you still stay in Beijing in the coming days?
Yeah, for this month I'm in Beijing, and actually I'm coming to Huizhou.
Coming to Huizhou. So the coming week.
Yeah, from 15 to 19.
Okay. It's very good news. I shall ask you some questions. I shall meet you and ask you some questions face to face.
Always.
Okay, now
it's fun. Yes,
okay.
Great.
Okay, thank you very much. Thank you very much.
I have two questions. So first one, you mentioned the radii of unstable nuclei in the beginning. In those forming systems you discovered, they are still a bound system. I'm curious, how do you define those unstable radii in this? Because, mathematically speaking, when a system is unbound, it will emit the particles and they will be different. Those radius will radius work.
Okay, that would be a one big talk. But I think that as long as matter radius is concerned, it is well defined from interaction cross-section. And this is interaction cross-section or reaction cross-section is well calculated by Radii. But these days people start to talk about proton distribution radius. That's changing process. This one is more problem because of the other evaporation or something. But reaction cross-section includes any reaction. So anything happens, it's in the reaction, and definition is clear. So matter radii, then you should do it. But the proton radii, it's with big error bars.
As actually how there are many applications for the tensor. But alternatively, there are other explanations, like the initial calculation also shows that the three-body interaction is important for those three lines. So how do you extract those effects from the experimental point of view?
I don't think we know now how to distinguish those three-body interactions or tensor interactions. But I think I'm telling tensor interaction because of those all systematically change are explained by one. And of course, three-body interaction also is necessary to make a bound state. And I don't know. I'm not really concerned on this is there any systematic things you can observe? I mean, right now, when you discuss three-body interaction, you have to rely on the theoretician. Just do some calculation and you need it. But unfortunately, we don't find any good systematic way experimentally yet for three-body interaction.
Professor Kachino have questions. Please.
Professor Tanihata, thank you. Probably I'm one of a little bit understand this theory because I have heard from you many times. Let me ask you a question. Probably this is a unique model, though not complete, which predict the next magic numbers in heavy nuclei. And you mentioned about the effect of R process. And my question is the following. Looking at the so-called R process abundance peaks, there is famous first, second, and third peaks, but in addition to that, there is a hill like a local maximum at a mass of 100 and 165. So you predicted 54. So do you really predict the peak as a function of mass number A, assuming that the proton magic number does not change?
I can do that, but I'm not sure about the accuracy or whether it is realistic or not. Because the R process is more complicated than just the magic numbers. We can discuss.
Oh, yeah. But anyhow, I recommend you to look at the so-called observed or R process peaks. So you can find many more.
Yeah, I can. At least I can find a mass.
Okay, good. All right. Yes, I'm waiting for you to come back. Enjoy. Thank you.
Thank you.
I'm Guo. So, yeah, thanks for your very elegant explanation. So one question is about, you mentioned the carbon 12 and oxygen 16 description. So, actually, for the past people, we are struggle about this because we cannot describe very exactly at the same time. So you mentioned the mechanism is from tensor force. My question is just from that shell for the ground state. So how do you can get the conclusion they cannot jump the high orbit and at the same time they have some tensor components? And you mean the carbon 12 and oxygen 16, they have very different tensor components, right?
Yes.
So, but in our interaction, we don't include explicitly, so we include the average effect. In this case, we lost something.
Yeah, you lose that one.
We lose the point. So, do you have some number about this carbon 12 and oxygen 16 about the tensor force particularly something or estimation?
What I'm not sure what is the good thing here. Not oxygen. No, not really carbon. Yeah. Okay.
Okay. Thank you. So, yeah. So if we want to really describe this in some sense better, of course, Poisson introduced three-body effective interaction. If you want to use, for example, two-body, and in some sense we can put an additional term, of course, phenomenal term. Like including some protein effect.
If you could make that model, that would be very handy and good. And also, I consider this alpha clustering.
Yeah.
It's really due to the tensor. Because alpha is the nucleus that is really, really bound by tensor interaction.
Yes.
So if you break it into alpha, you gain a lot of tensor interaction. The oxygen 16 is blocked, but if you put four alphas, then you gain some tensor energy. So actually, that would be a driving force for making cluster in oxygen 16. And so I think this clustering and tensor should be very much related. You may discuss with Horiyuchi about that. Yeah.
Now I think also we are trying to include this effect.
Yeah.
Let's talk about the question. So it means if the tensor is actually well fitted, only using one interaction can explain.
I think so.
Yeah. It's just that.
Yeah. That I'm really waiting for this algorithm calculation to go to oxygen 16, but they are spending more than 10 years to go from carbon to oxygen 16, but
the last question. So you emphasize the importance of tensor interaction. Like using this type of interaction, you can explain many new neutron-rich matching numbers. So can these neutron-rich matching numbers accommodated in the traditional shell model based on the spin orbital coupling? Can these new matching numbers accommodated by this traditional shell model or not?
traditional shell model cannot.
Cannot. Because in the traditional shell model, I find that only the spin orbital coupling is placed in natural number.
Of course, if you change the effective interaction in the region, then of course you can do it. But if at least in one major shell, you don't want to change effective interaction, right? And in that way, you cannot. And this is another mystery I explain with this, is that if you make effective interaction above oxygen 16 in SD shell, you can make very good effective interaction. And because above oxygen 16, it's all nuclear-nuclear interaction. So it should be okay also for FP shell, right? If you include SD and FP shell, all of them as a valence nucleon, those should be same interaction. But it's not. Once they include this FP shell, interaction is completely different from SD shell interactions. Why? Because those blockings are not included in shell.
Is there any more questions from online? So let's thank you, Professor Tanihata again.
Okay. Thank you very much. Thank you.